Hey everyone, my name is Sahil Patel, and as I was learning about microprocessors, I glanced upon a really amazing and in-depth topic of how NVIDIA and its GPU, the graphical processing unit, works, their processors and their architectures. So welcome, and I'm going to talk about various topics and how NVIDIA has made us explore and enjoy the future of processors. So I'm going to talk about the topics in gist so that it is not it is enjoyable and you guys can explore the in-depth topics specifically. So let's start. For the outline of the presentation, I have included all the topics that I will cover. That is the motivation of why NVIDIA is the legendary uh, industry and it's grasping the power of GPU in the world. Its many applications. What is GPU? The GPU theory and history, differences than CPU, revolutionizing the computing, the GPU architecture, the basic only. The NVIDIA CUDA, the CUDA environment, and parallel computing and the graphics pipelines. So coming to motivation. So why NVIDIA? Why GPU is like the world of legacy here? So uh, you can see in these pictures, you can see how AI, how machine learning, deep learning is like the future of the society. The like in the half the century, AI will be like in every aspect of the industry, in every industry, it will transform. Self-driving cars, DNA, medical preferences, engines. In all the engines will be stronger and powered with industrial materials. So how will that happen? It will happen with a computing model of GPU that will be running in deep learning. It will be applied in deep learning. So computers will be able to learn data and write software that is too complex for people to code. It will be able to learn that pre independently with itself in itself only. Yeah. So coming back and going forward, what is GPU? So GPU can be described as a electronic circuit used to accelerate and create images at a greater speed than the CPUs. The GPUs are used in embedded systems, mobile phones, computers, workstations, everywhere. There, there are so you can see in the image that there are many components of the GPU. The GPU is placed on a video card which contains its own memory and display interfaces. And it was first used as a individual term and worldwide it got its dignity in 1990s. Coming to the theory and history of GPU. So GPU, graphical interface processing unit, is as we discussed, it is an electronic circuit, and this term was popularized by NVIDIA in 1999. GPU was first introduced in 1970s, and it was first stood for graphical processor, and it was used for graphic manipulation and outputs. But later in 1994, it was used with Sony and Toshiba companies as in their gaming consoles. But it was popularized by Nvidia in 1999, who marketed the GeForce, world's first GPU, and gave it that title. It was a single chip processor which integrated transform, lightning, triangle setup, clipping, rendering engines, etc. And similarly, and then rival companies also used the terms and started the GPU market. Modern GPUs are very efficient, as we all know about how NVIDIA, AMD, they all Ryzen series, GeForce series, they all have touched the skies with the GPUs and processing speeds. Their highly parallel structure makes them more efficient than general purpose center processing units (CPUs) for algorithms that process large blocks of data in parallel. In a personal computer, a GPU can be present on a video card or an embedded on motherboard. In certain CPUs, they are embedded on the CPU itself. Let's move forward. So the key aspects and differences than CPU. So we talk about the difference between a CPU and GPU. So I it came to my mind about a video that I saw about NVIDIA, which was breaking the myth between the speed capacity between a CPU and a GPU. See, if you search about it, you will find the video where how NVIDIA in a conference on stage proved with the help of paintball robot that they in first they shot for the CPU they shot on a screen on a white screen they shot paintballs one after the other like 15 to 20 paintballs to make a small smiley face. And for the GPU, you all know that how graphics and images can be processed at a very large speed in GPU. So for GPU, they showed 10,000s of paintballs are shot to create a beautiful Mona Lisa simultaneously. In for that CPU, the smiley face was made by one after the other paintballs were shot, but here it was simultaneously. So we can figure out the difference between a CPU and GPU in for fun way. Now coming to key aspects, GPU has more throughput, more importance than latency, and it is extremely parallel. The parallel computing is more on thought in GPU than CPU. In CPU, there is sequential coding, and in GPU, there is parallel coding. Different pixels and elements of the image can be operated on independently, and hundreds of core execute at the same time to take advantage of this fundamental parallelism. So coming to throughput. What is throughput? The throughput refers to performance of tasks by a computer service or device over a specific period. So this shows how GPU can be used to just boost the performance of a processor, memory or network communications wherever it will be used. So coming to just a follow-up of the motivation which was discussed before, like how artificial intelligence and AI and cars are used. So the NVIDIA GPU revolutionizes computing, and it revolutionizes modern worlds also. All the gamers should know the how simulating human imagination is used, how creating amazing worlds, how the NVIDIA different components like Quadro, GPUs, and everything has done a remarkable work in creating the open worlds in games for visual effects for NVIDIA technology to make a vision a reality. For creating amazing worlds, today's gaming industry is fueled by a steady stream of blockbuster titles. These NVIDIA GPUs are the engines that make these possible, and the NVIDIA tech makes games more graphic rich and immersive. All thanks to the NVIDIA GameWorks and other Unreal engines. Because of all that, it is possible. So discussing about it more, we can see how GeForce has become the world's largest gaming platform with a $1 billion computing gaming industry, and it transforms everyday PCs into powerful gaming machines and creating virtual realities also. NVIDIA GPUs power intensive VR, and these headset makers and game developers create amazing VR devices, which in turn is the future of the world which is heading over to metaverse and all that. It also revolutionizes computing like the CUDA programming which has come in 2006 and which will power for general purpose computing a powerful new approach to computing. It also powers life-changing scientific discoveries and the HIV research, CT scans, which will be powered with GPU. Then it will reduce patient radiation exposure, and produce high quality imagery to determine the absolute specific disease or cure which doctors can recommend. AI researchers also discovered the NVIDIA GPU, which will, like, all of us have heard of ImageNet. ImageNet has won the internet by, like, Google and Facebook have broken the records by using ImageNet, and they have reached about 96% uh, of result of detection accuracy, which was earlier it was like 74 or something in 2010 era. The world's first AI used NVIDIA and used in supercomputers also. Using NVIDIA graphics GPUs has made it like a ultra smooth, ultra efficient, and ultra imagery computer. Amazon, then brain of intelligent machines, IoT, brain of AI factories, robots will be used in the supply line to conduct and create the machinery and the cars and all that. So we know all this powers our minds of how NVIDIA has shaped our surroundings of tech. Let's move forward. Now, coming to GPU architectures. So here you can see two examples. One is NVIDIA GeForce 6 series and another is NVIDIA GeForce 16 series, which came in 2019. The NVIDIA GeForce 16 series uh, is is as you know, the GTX 1650, 1660, all that one, 1650 Ti is based on Turing architecture, and the earlier one is based on Curie architecture. So let me first tell you about the GPU architectures. So NVIDIA has a complex architecture, but let me give you an overview. So NVIDIA architecture is a single instruction, multiple data stream architecture. As you know from the Flynn's taxonomy, so this scheme array of hundreds of math processing can work in parallel and crunching more numbers. So the computational model of 3D graphics as well as computer vision and deep learning is the same math algorithm that is applied repeatedly to thousands of millions of data items, and all that can work simultaneously and efficiently in a short time. The SIMD, that is the single input multiple data stream, is a parallel computing algorithm and is a computing model that can efficiently, by using one CPU, control 32 math processors in parallel, with each processor doing the exact same step but to different data items. So this way, we can get in, instead of doing 1 to 10 gigaflops, that is billion floating point operations in a normal CPU, a GPU SIMD will have 32 to 320 gigaflops. So we can see how much more processing speeds we can get by using SIMD architecture. Below image, as you can see by this image, you can see the NVIDIA card with two graphic processing clusters, each with four streaming multiprocessors. SM is multiprocessors, each with four streaming multiprocessors, and we can see that it will give us more cores and more processing speeds math processors. It turns out that the speeding of the math throughout creates new problems, main one being efficient memory transfer, and the new ones to be extra extra deep learning. As we know about SIMD, that is single instruction multiple data streams, it is a type of parallel computing and where all processing units execute the same instruction at any given clock cycle, and it supports multiple data and best suited for specialized problems and high degree of regularity. And we like in Flint's taxonomy, there are also other like a single instruction, single input data structure, multiple instruction, single input. But we are using parallel computing, and in that there is single instruction, multiple data streams. We are using multiple instructions simultaneously. So SIMD is a better processing speeds, gives better outputs. So now let me switch to another source and show you about different architectures throughout the history of NVIDIA. As you can see about a brief history of NVIDIA GPU architecture. It all started from 2000, wherein first the Kelvin architecture came in, where the NVIDIA's first GPU microarchitecture was designed, when the GeForce 3, GeForce 4 series was released. And it was success by Rankin. Then it was success by Curie, which was a first generation for NVIDIA for video decoding, video encoding, and it also simultaneously doubled the amount of RAM to a higher memory output than the previous architectures. Then came Tesla in 2006. Uh, which both improved the speed, and a quadro line of GPU was designed which powered GeForce 8, 9, a lot of series which became very popular, and it designed a great line of success. Then came the Fermi architecture. Fermi architecture supported 512 CUDA cores and more RAM, which was ability to partition cache and shared memory. Kepler architecture design came in 2012, which improved the Fermi architecture with more features. Every architecture came with more improvements, so the modern architectures are the ultimate in terms of improvements. Maxwell architecture released in 2014, which was a successor to Fermi. According to NVIDIA, the first generation Maxwell GPUs had these advantages: more efficiency, more dedicated shared memory, dynamic parallelism support, etc. Then came the Pascal architecture. Then came Volta architecture. So this is the Turing architecture, which was released in 2018, and which in turn is the current present uh, worldwide used GPU processors in laptops like the 1650s, the GTX series, RTX series, which shaped VR, virtual reality, heavy application computationally. Ampere's Ampere architecture is the beginning to hit the market. It is like a it is like touching the skies uh, uh, with its third generation NVLink. It powers the NVIDIA GTX Titan series, which, as the name suggests, breaks all the records. The 3000 series, Titan series, etc. So we can see the micro architectures, the designs that came in NVIDIA, and how it shaped the next architecture, how improvements came in the next architectures. Coming back, let's talk now about NVIDIA CUDA. So NVIDIA CUDA is a revolutionary designed architecture by NVIDIA which supports image processing. It has many applications on different drivers. It uses programming. It is used in programming in C++, Python for runtime efficiency in deep learning, machine learning. It is used in different drivers for shader programming. It is used in OS kernel level. It has OS kernel level support. It uses drivers. It uses kernels and functions for parallel computing, programming, etc. Now this is the architecture and the image which shows the different APIs and integration which all is used in CUDA. So what is CUDA? It is developed by NVIDIA and released in 2006 as a worldwide SDK. As a SDK, it was released in 2011. it uses model complex problems and achieves up to 100 times performance of the CPU if used correctly. If the algorithm that is used or the CUDA toolkit which is used is specifically used for a perfect task, then it can achieve up to 100% more accuracy. Uh, as you can see by the above image, like the programming approaches, the development environment used in CUDA, parallel computing platform, the open compiler toolchain, the hardware capabilities, there are much more, but this is just a prerequisite of how and what happens in CUDA, like the SMX compiling, dynamic parallelism, all this happens and makes our code more more efficient, more processing speeds, touches the skies. The machine learning and deep learning uses CUDA as a toolkit in the libraries as a prerequisite to run. The TensorFlow GPUs always run with help of CUDA. How does CUDA work? So CUDA basically works with three small steps, that is copy input data from CPU to GPU, load the GPU and execute caching data on chip for performance, and copy the result from GPU back to the CPU memory. So as we can see, that is a dynamic process between CPU and GPU. Let's go ahead. So next is CUDA and the environment and programming abilities, features it has. So CUDA full form is Compute Unified Device Architecture, and it is a application programming interface, that is API, that allows graphic GPUs for general purpose and for general purpose computing. It has parallel computational elements for execution of compute kernels, and the programming abilities are can be designed in languages like C, C++, Fortran, and the APIs can be used by specialists for parallel programming, which requires advanced skills in graphic programming. The CUDA powered GPUs can support OpenCL, OpenACC, all these frameworks and APIs which can high power our data model, our deep learning, machine learning models, and make them more accurate reaching. The major features are that it is a specialized addressable demands of real-time high resolution, and these tasks can be performed by CUDA easily. In 2012, GPUs had evolved into high parallel, unit parallel, multi-core systems, and these efficient manipulation of large blocks of data. And this design is more effective than general purpose CPUs for algorithms where large blocks of data are done in parallel. So CUDA can help here a lot. So coming to some terminologies of what parallel computing and graphics pipeline is. So parallel computing, as the name suggests, we break down larger problems into smaller, and as a result we can simultaneously, via shared memory, we can combine the algorithms, we can combine the results simultaneously and give outputs at a great speed than the CPUs. So graphic pipeline is a term which comes in GPUs. The left, the image on the left shows the different components of the GPU's internal components. The bus interface, the graphics memory controller, GCA, VPA, the display interface. And all this comes in the graphics pipeline. The pipeline at the very highest level can be broken into two parts, the CPU and the GPU. The CPU optimization is a critical part of optimizing your application, and it will not only focus of this chapter because much of the optimization has little to do with graphic pipeline. This image on the left shows the GPU. There are a number of functional units operating in parallel, which essentially acts as a separate special purpose processor, and a number of spots where the bottleneck can occur. These include vertex and index fetching, raster operations, fragment shading, triangle setup, rasterization, vertex shading, etc. Transformance and lighting, etc. Vertex shading is already transform and lighting, geometry commands, textures, frame buffer, etc. This on the image on the right shows how rendering can be done with the help of GPU and CUDA with the right tools. Coming back to this picture, this shows on the right image on the right shows about vertex about different properties and how it or simple basic images of how it happens. Vertex shader, generating primitives, pixel shader, testing and mixing, etc. And the graphic pipeline methodology is simple. Optimizing without proper bottleneck identification is the cause of much wasted development effort. So we formalize the process into identifying and optimizing the loop. We first identify the bottleneck and we optimize the bottleneck stage, reduce its workload until performance stop improving or until you achieve your desired level of performance. And then we repeat the above two steps so that the desired performance level is reached. These images also show different features, image processing features that can be achieved with the help of GPUs. The vertex shader, shape assembly, geometry shader, test and blending, rasterization, vertex index lists, the TL that is transform lighting, rasterization, etc. etc. I hope all that showed us about all the advances and learning of GPU, just the gist so that it is enjoyable and you can go into the depth. So coming to the input and output of GPU. So what goes into the GPU and what is the output that comes out of the GPU into the CPU and the display screen. So the inputs are the vertices, the lighting data, the texture data, and the output is the frame buffer, and which is placed in specific sections of graphic memory and which contains RGB values, and this data is sent directly to the display. Yeah. So as I discussed earlier about some architectures in the NVIDIA, these pictures show about a Fermi architecture, which was released around 2010 and it was successor to the Tesla. And as we can see, it powers 400 series and 500 series of geforce, and it has 32 CUDA cores and 3 billion transistors and all that stuff. RAM RAM and streaming multiprocessors, and host interface connects the GPU to the CPU, and the Fermi memory architecture is in detail. These all terms can be associated with all the architectures because these are terms and are the components of the GPU. So there is SM, that is the streaming microprocessor, the L2 cache and all their features, the L1 cache. In GPUs, the cache size is less in than CPUs. The global memory and all these components are connected and intervened in processing, so we get the display. So coming back to some different where we discussed about the CPU and GPU. So a image which shows specifically how both are differentiated. CPU, it optimizes for low latency, whereas GPU, it works for data parallel throughput. And we can see from the image how ALU is more in GPU than in CPU. And on the right hand side, there is a image of Tesla architecture and the different features it comes with. The 128 threads per processor and SP processors at these many gigahertz, 1.5 gigahertz. All these terms, the SM, the different cache, all these can be explorable and in depth known to know how the processing speed is achieved, how the computational requirements are done. This, the image shows the Tesla streaming multiprocessor, which shows SM, I cache, the MT issue, C cache. All these have the SM has 8 thread processors, 2 special function units, multi-threaded instruction units, and how this Tesla has achieved high processing speed and powers the GeForce. It shows that the concurrency thread shared data, low latency load store. So we saw about various microarchitectures. We saw about the motivation of how NVIDIA is changing the world of modern computing, modern graphics, modern tech. So if you want to know more about this, you can always go to the NVIDIA documentations, the official documentations and the official website, and which shows how CUDA cores are efficient, that CUDA toolkits, that CUDA high power systems, which can be also downloaded and used in our deep learning and machine learning models and projects, which we design in college and stuff. So thank you, and hope you enjoyed learning with me. And feel free to explore every topic that was discussed in depth, in detail. And I hope I made you aware of NVIDIA, that every laptop has a graphics card, which makes you wonder about how how the work happens. So this is it. Thank you guys. Hope you enjoyed.